So we will look at portfolio optimization. So you have capital C, and we need to invest it into N stocks. Let's say the current values are, I'm going to call it as S1 of T, S2 of T, etc., Sn of T. In other words, if I plot this S1, which is the actual stock value, it may be something like this. So against time. And similar, so that's S1. S2 could be also something else. So this is S2 of T, actual stock value. And S3 could be something like this. So this is S3 of T, etc. So there is a lot of fluctuations. So the question is, how do you distribute the capital into these things? What is the optimum? So you could say fraction of some fraction A1 goes into here, A2 goes into here, and AN goes into here. Of course, the fraction has to be positive, non-negative, or strictly positive if you are going to use all that. And then you can clearly see another condition is all these AIs, I equal to 1 through N, should add up to 1, because the total money we want to exhaust it. So portfolio is like this. You want to have so this may be S1 by S1, and this is, let's say, S2, Sn, etc. So AN. So of the total money that is coming in is A and C. The fraction fraction multiplied by the total capital. Similarly, this will be A1C, etc. So what is unknown? Of course, this is given. Let's say we did some research and we also have figured out where to invest. That's also given. So rather than, the whole idea of portfolio is rather than invest in each of them separately, we want to hold a combination. So the combination is going to be determined by how much money we are going to invest into each of them. So the only unknown quantities are these AIs. So the question is, how do you select it? So we do need some criteria. So let's say we decide to buy it at some time T1, and we can look at what happens at time T2. So let's look at any one stock. The price here is S1 T1, is the value of the actual stock. And since this is the ith stock, we have decided to invest so much money into it. So the number of stocks we could buy, NI is going to be total money invested divided by the current value. This is the number of stocks, number of ith stocks in the portfolio. So then when you, if you look at it at a time t instant, the portfolio value, of course here the value is A1C because the entire money is invested, whereas here the value is going to be whatever is the number of stocks divided, multiplied by the value of the stock, the value of each stock at that point. So if you want to look at the gain for this particular gain or loss, this is your current value, this is the value that we invested in. So the gain GI could be positive or negative, is NI multiplied by the current value minus the original money invested, which is NI multiplied by the initial value, or it is simply CAI. This is the initial value invested. This is the current value for that particular stock. So notice that if I plug in for NI, NI is CAI, so this is CAI divided by SI of T1 multiplied by SI of T2. minus CAI. So if I pull out the CAI, this comes SI of T2 minus SI of T1 over SI of T1. Notice that this quantity in the parenthesis has a meaning, because this is the final value minus initial value, whatever value we bought, divided by the initial value. So this is the return on the particular stock. So if you bought Apple at $100, and if it is 120 now, 120 minus 100, that's 20 divided by 100, so that's 20%. That's the return. So we really only care about this return, because if you had bought a stock at $1 and it is $2 now, the return is 2 minus 1 over 1, that is 100%. So obviously that's a better investment than the Apple investment. So what I'm trying to say is, for investment purposes, this quantity is what is important. This is the return. Return over that duration. Remember, you only care about when you buy and when you sell. So this is the return of the ith stock over, of course, this duration T1 to T2. When you are, this is when you buy, this is when you sell. So if you want, you can write this as CAI-RIT. So this is the gain on the portfolio due to this. So portfolio itself is going to be the sum of all such gains, I equal to 1 through n. So this is going to be sigma CI AI RI of T, I equal to 1 through n. So this is the portfolio. All right, so the question is now, how do you select these constants? What are the criteria? So this is the, of course you want to make money. So the expected, if you look at the expected value of the portfolio, that's going to be the average return, because this is the return, average return over all the stocks. So that's going to be C sigma AI, expected value of RI of T. And let me call this quantity to be mu I. So this is going to be C sigma AI mu I equal to 1 through n. We can take C to be 1 so that we don't have to carry around. So this is the mean value, or the return on the portfolio, average return. Of the portfolio. Of course, we want this number to be high, but what you see here is there is a lot of variation on each of these stocks. So especially if this money is very large, let's say C is $100 million, so then we would like the total portfolio to be reasonably stable with respect to the variance. So we also need a measure for its volatility. That's, I think in this context, it's going to be the variance of this quantity. So that's going to be the variance of P, which I'm going to write it as sigma squared. So that's sigma squared. That's going to be expected value of P minus mu P, the whole squared. So now we can substitute for, so let me do it here. We can substitute for P there and see what that comes out to be. So if I call sigma squared to be the variance of the portfolio, so this is going to be expected value of P minus mu P, the whole squared. So P is given to be, so this is sigma AI RIT, that's P. So this is expected value of, so P is going to be summation AI RI. Mu P is sigma AI mu I. So this is sigma AI Ri minus mu I equal to 1 through n, the whole thing squared. So that I can expand this as double summation Ai Aj, expected value of Ri minus mu I multiplied by Rj minus mu j. But this is the covariance of Ri comma Rj. So I'm going to call this as, let's say, Cij. So the summation is on I and j. So this is going to be double summation I equal to 1 through n, j equal to 1 through n, Ai, Aj. Remember, As and Ajs are not only real numbers, they are non-negative numbers, Cij. And this whole quantity being the expected value of a positive number, this is non-negative. In fact, it's positive. So the question is, what do we do now in terms of selecting the AIs? And here is the, I think, idea due to Markowitz from the 60s, I believe. That is, once again, if you look at each stock may have a lot of volatility. So even if you plot various returns, the returns itself may be high, but it may be also, you have a lot of volatility. So variations, right? So the idea, remember, the portfolio itself is here somewhere. Portfolio is a sum of all the returns from each of these stocks, each stock being weighed by a quantity AI, a fraction. AI is, of course, between 0 and 1, and that's the unknown. So idea of Markowitz is that you select these constants so that you are not controlling the stocks, you are not running these companies. But where you have control is in selecting these constants AI. All you care is your portfolio. Your portfolio is going to vary because each of these returns are going to swing around. So control what you can control, which is the AIs. So the criteria due to Markowitz is try to find the AI so that the volatility, which is represented by the variance of what you are holding, which is the portfolio, be as small as possible. So that's minimize the volatility. This you can also call the volatility of the portfolio that you are holding. So you are only interested in what you are holding. So the whole idea is that hopefully the portfolio should be like this. The variation is small, and if you did your homework, your stocks, your total portfolio will go up. So what to add, you have to do some legwork so that your prediction is that things are going to look good. So what we can do is to minimize this variation. There will be some fluctuation, but you don't want all this violent, a lot of volatility. So minimize portfolio volatility. Essentially, you minimize the variance of the portfolio, the minimization being on the AIs. So this is an optimization problem. We have the expression for the variance here, but this is a constrained optimization because we also have the constraint that at the end of the day, when all the AIs should add up to 1. So again, you have to look at the problem that he is trying to solve. He is only solving what he needs to solve. He is not trying to run the entire market. His goal is only on what he is holding over that duration. So that's how you come up with the portfolio. Of course, you would like this gain to be as high as possible, but that you remember what sorts of stocks to choose or commodities to choose is an earlier question. So hopefully you have done your research and you have figured out that you want to invest in this particular one because the research shows that things are going to, that particular item is going to do well. So this uptick is expected. Otherwise, if you don't expect it, don't include it in your portfolio. But once you decide to include in your portfolio, how much of it, how much fraction of the money should be invested in it. So do it in such a way that the volatility is reduced of what you are holding, not the whole market, just what you are holding, right? So we can look at this as a constrained optimization problem. So that is volatility minimization. As I said, this idea is due to Markowitz, and so portfolio volatility minimization. So minimize over AIs the variance, plus we will put it as a Lagrange constraint. The summation sigma AI should add up to 1. So if I substitute for the portfolio variance, that's double summation from there, AI, AJ, Cij, I equal to 1 through n, j equal to 1 through n, minus lambda summation AI minus 1, I equal to 1 through n. So we can also write this in matrix form and do it quickly. But let's say we do this. So easiest way is you take the derivative with respect to AIs. So that gives you summation j equal to 1 through n, AJ Cij minus summation lambda. There is only one term here, a particular AI. This should be equal to 0. And you have for I equal to 1 through n. So this is linear set of equations on the AIs. And if you put it together, we can write it in a matrix form. It's easy to see. And this is going to be C11, C12, etc., C1n, C21, C22, etc., C2n, etc., Cn1, C22, etc., Cnn. This is the variance covariance matrix. So I'm going to call this R. This I'm going to call the A vector. On the right side, you have lambda 1, 1, 1, 1, 1. So I'm going to call the standard notation E vector. So this whole thing now, so remember Rij is this entry. So Rij, ijth entry is expected value of Ri, the return, ith return minus its mean multiplied by Rj minus mu j. So that's the covariance matrix. When I equal to j, these are the variances of each stock. So both the variance and covariance comes into play. So this equation now reads as Ra equal to lambda E. So we can solve for A here. So A is of course R inverse, lambda is a constant. So that's lambda R inverse E. And the question is, how do you decide lambda? So that's easy because all the A vector, all the entries should add up to 1. In other words, E transpose A is nothing but sigma AI. That should be 1. So we can substitute for A here. So that's lambda multiplied by E transpose R inverse E. It should be 1. So we can solve for lambda. Lambda is 1 over E transpose R inverse E. So if you substitute it here, so you get the optimum A to be R inverse E, which is a vector divided by E transpose R inverse E. This is a scalar quantity. So the optimum, A optimum, which is going to be a vector like this, A1, A2. So we have the solution is going to be R inverse, which is a matrix multiplied by a vector divided by a scalar quantity. This is for only make sure that all the entries add up to 1. But the one condition is that all the entries of this, each of these entries should be non-negative. So if you take an arbitrary set of covariances and take its inverse and multiply it by the unit vector, there is no guarantee that the entries in this would be non-negative, all of them. So that's so there we have to pause. Either you have to take a reshuffle and take a new set of stocks, or you have to do a suboptimal solution with the constraints that the AIs also should be. Here I haven't imposed that condition, even though all I'm saying is all of them should add up to 1. And there are this additional condition that all the AIs are positive has not been imposed here. So that you can do it as a linear programming problem. And in any case, it's going to be a suboptimal solution. And that leads to and that will give you the optimum AIs. Another possibility is that you could say that I'm going to select those stocks to start with, so that's going to be a difficult problem where R inverse has all positive entries. So this is an interesting problem. How do I come up with a covariance matrix whose inverse, so R inverse has only non-negative entries. Remember, you start with R, so those covariances could be positive and negative, and then you want to select a stock such that R inverse, because if R inverse is non-negative entries, this is non-negative because it's all 1, 1, 1. So this will be a constant, positive constant, then this will be a, so you could call them tight stocks. Tight stocks are such that their inverse of their covariance matrix has non-negative entries. So let me give you a very easy to construct that example for a 2x2 case. Suppose I have two stocks, S1 and S1 of t and S2 of t, or the returns R1 of t and R2 of t. So two stock case. So I have R1 of t and R2 of t. So the covariance matrix is only 2x2. So this is sigma 1 squared, which is the variance, sigma 2 squared. This is rho sigma 1 sigma 2. This is rho sigma 1 sigma 2. Now if rho is such that, or suppose rho is negative, then you can see that because R inverse is going to be 1 over 1 minus rho squared multiplied by sigma 1 squared, sigma 2 squared, then sigma 2 squared, sigma 1 squared, minus rho sigma 1 sigma 2, minus rho sigma 1 sigma 2. So you can see if rho, this is R inverse. So if rho is negative, in other words, if the two stocks are moving in the opposite direction, then R inverse is guaranteed to be this is a non-negative matrix, or a matrix with positive entries or non-negative entries. This is not non-negative definite, just entries are non-negative. So if the two stocks are negatively correlated, minus rho will be positive and everything will be, all the four entries will be positive. And you will know how to split the money because A1 will be positive, A2 will be positive. You can just work it out from here. So that's the only case which can be easily done. Otherwise you have to go through one way is you go through a search and find out a set of stocks which are tight stocks. So very easy to find two tight stocks because You just take two, so which also makes sense. If you are going to invest in two stocks, select the two of them so that their correlations are in the opposite direction. Both of them do not go up and down in the same at the same time, so that their total variance. Another way to see is that if you have two stocks, the variance of a portfolio is going to be A1 squared, which is sigma 1 squared minus 2 or A1. A2 is 1 minus A1 multiplied by rho sigma 1 sigma 2, because the combination is A1 R1 plus 1 minus A1 R2 plus 1 minus A1 squared sigma 2 squared. Notice that this term is positive, this is positive. If rho is negative, this will be a negative term and the variance decreases. If rho is positive, of course the variance increases. So if you want to minimize if the stocks are, if the rho is negative, then the optimum solution is given by here. Otherwise you have to go through linear programming techniques to find the suboptimal solution. So to continue maybe a little more on this portfolio optimization. So we have a stock, this is where you buy, and whatever reason we decide to sell here. So these are other questions, when to buy, when to sell. So the two quantities that are important to us are the buying price and selling price. And as we saw, this difference is S of selling minus buy, T1. This ratio is what is important. So I'm going to call this the percentage return or the gain. And what we saw that in the portfolio, if you have C, how do you allocate your money? A1, A2, etc. And these are the fraction of the money that goes into each one. And see, so the portfolio we saw that is going to be, so let's say C is 1, sigma AI Ri of T. And so the mean value of the portfolio is expected value of P. This is summation AI, expected value of Ri of T. So this is the average return on the ith stock. So let me call, this may not be stationary, but over this duration, let me call it to be mu I. So this is from your research. If you are buying it here, you have some reason to expect that on the average, whatever, 5% or 7%, etc. If you're saying on the average it is going to go down 10%, then don't put your money into that one, especially if you're going to get in here and get in out. So your research has to project. So this is sort of confidential information that you have collected. So you could write this as summation I equal to 1 through n AI mu I. If you want, you can write it in a vector notation as A transpose mu, where A is going to be A1, A2, etc., AN, and mu is going to be the various projected returns mu1, mu2, etc., mu n. So these are after all projected returns, but if you have a projection, the question is how do you select these constants AI? So once again, we can look at the volatility also. In other words, the portfolio volatility. So I'm going to call it the sigma p squared. It's a fancy name for the variance of P. So P is here. So using this notation, we can write this as A transpose R. So A is already defined. So if you define R of T as the various returns, R1 of T, R2 of T, etc., Rn of T. So that's the vector. And the variance is expected value of P minus mu P the whole squared. So P is A transpose So here A transpose RT minus A transpose mu. So this is RT minus mu, or the whole squared. Because it is square, we can write this as P multiplied by P again. But this is a scalar, so I can write this as A transpose RT minus mu. That's a scalar, so multiplied by its transpose is the same thing, but its transpose is going to be RT minus mu transpose A transpose. That's the transpose of this. But notice that the expected value comes only here. So this you can write in the vector notation if you want expected value of RT minus mu multiplied by RT minus mu P. And this is a matrix capital R multiplied by A transpose here, A transpose. So this is capital R. So we get this expression that this is equal to A transpose RA, where Rij is, we had it before, expected value of Rit minus mu I multiplied by Rjt minus mu j. So this is the covariance between the returns Rit and Rjt. And R being a variance covariance matrix, it will be at least a non-negative definite. Let's say we picked up stock so that the R is actually positive definite stock. So that's another criteria we will need, because even in the Markowitz solution we need an R inverse. So R has to be full rank, or the entities have full rank, so that R is, the covariance matrix is full rank. So this is the variance. Variance is also positive or non-negative definite. Now, if you say not, so the Markowitz criterion is to minimize the portfolio volatility. That's the Markowitz criterion. So the whole logic there is you do what you can. The selection of A is based on the minimization of the volatility, and in terms of the gain, you plug it in and you take what you get. So hopefully you have done some research so that each of these gains are, projected gains are positive, and you overall gain, you take what you get. Now suppose you want to bring in into your criterion the fact that you want the gains to be as large as possible, and at the same time you want to minimize the volatility. Then we can borrow concepts from match filter. So rather than look at, so we look at something like a signal to noise ratio, which is the portfolio gain over the variance of the portfolio. So try to maximize this quantity. So we want the gain to be as large as possible, and we want the variance to go down. Variance represents the volatility. So rather than concentrate on this, which is minimization of the volatility, we could try to maximize the ratio. So if I substitute for mu p, notice that I put mu p squared because that will end up, mu p already we have an expression for both. So this is our mu p, and this is our, this quantity is our variance. So mu p is going to be So mu p is A transpose mu over A transpose R A. So this is a standard problem how to, so maximization is on A. So if R is positive definite, I can write here, I can say I introduce R to the power half, but I take off R to the power half. And then I have mu here. So nothing, because this is identity. So this thing squared divided by A transpose or A. Now let me call this quantity to be B transpose and this quantity to be C. So B is going to be R to the power half A and C is R to the power minus half mu. Because B transpose is going to be A transpose R to the power half transpose, but R is already Hermitian, which means R has the property that R is the same as R transpose. You can see that Rij is the same as Rji. If you flip I and j, you get the same thing. So from Short's inequality, we also have this relation, right? B transpose C is of course less than or equal to B transpose B multiplied by C transpose C. This is true for any vectors. And you get equality when B is of the form KC or C is of the form one way or the other way. So you have equality here when B equal to KC. So we can try to apply this here. So we have, this is of the form B transpose C squared over A transpose or A. You will see why I introduced this term, but this is B transpose B. This is less than or equal to B transpose B multiplied by C transpose C over A transpose or A. But now if you substitute for B transpose, which is here, I have A transpose R to the power half, then B, which is here, R to the power half A, and then C transpose. C is here, so C transpose is mu transpose R to the power minus half, and then multiplied by C, which is R to the power minus half mu. And the whole thing divided by A transpose R A. But notice that this quantity R half is R. Similarly, this quantity is R inverse. So we have, this is, in the numerator we have A transpose R A multiplied by mu transpose R inverse mu over A transpose R A. So this is a standard practice in match filter theory and signal processing. So notice that this cancels and you get the answer to be mu transpose R inverse mu. So this is the maximum value of that signal to noise ratio. So remember, the goal is to figure out A which will maximize this ratio. So why maximization? Once again, we want this gain to be, gain of the portfolio to be as high as possible, and at the same time we want the variance or the volatility to be low. So this is the volatility of the portfolio, and this quantity is the portfolio gain. So we want this quantity to be high and we want this quantity to be low. That's why we put it in the denominator. So if you maximize the ratio, both has to happen. And of course we would like to be greedy. We would like, look at here. So this value is always going to be less than or equal to, because of this this value. So this must be the maximum value. So question is, when can you make the left side equal to right side? This is the condition. You will get equality here if B is made proportional to C. So we have to make, so if you go for equality, B equal to C. So B is R to the power half A must be proportional to C. C is R to the power minus half mu. So I can bring this R to the power other half and we get optimum solution to be K R to the power minus inverse mu. So the question is, what is K? K is easy because all the A's should add up to 1. This is A transpose, E transpose A should be 1. So E is the vector of unit vectors. So if you put in this condition, E transpose A is here, K multiplied by R inverse mu should be 1. So we get K to be 1 over E transpose R inverse mu. So finally, if I substitute it here, we get A, the optimum A to be very similar to the Markowitz solution, except that he had E's here. So we have E transpose R inverse mu. So the mu's were the projected returns, R is the variance covariance matrix. And so this is the, and again the same problem. If R inverse has got negative entries, it's possible that some of these entries will be negative, and then either you replace those stocks with something else or you go for a suboptimal solution. Two stocks, of course it will work. If you take the two stocks to be opposite correlation or negative correlation, then R inverse will have positive entries. So once again you could say that if you have a set of tight stocks, by which we mean a set of stocks for which R inverse has non-negative entries, then this is going to give you a different A. This A is not going to be the same as the Markowitz one, because the Markowitz solution was, optimum solution was R inverse E divided by E transpose R inverse E. Remember, E is all this, all one vector. So if R inverse has got non-negative entries, this will be, so this let's call the SNR solution. So here the interesting thing is, instead of all ones, we are replacing that by mu1, mu2, etc. Remember, mu is this projected returns. So you may say, I don't know the projected returns, but that's where you need to spend some money and do some research, and so the research people will come back and say, these are the projected returns in this, and if that projection doesn't work, you fire those people, right? So anyway, that's the mu's. So here we are using this projection to improve upon A. Hopefully it is an improvement, whereas here you are saying, if I don't know anything, I'm going to take all the returns to be, you can see the sense. If you don't know the specific to be 5%, 7%, etc., I'm going to take all of them to be uniform, same returns. But if you have a bit more information, why not use it? So that's the update on this. So bottom line, to summarize, the Markowitz solution is, so this solution leads to ASNR, optimum solution, is R inverse mu over E transpose R inverse mu. So this is a scalar just for scaling versus a Markowitz solution, which is R inverse E over E transpose. So the denominator is only for scaling in both the cases, because if you add up all these entries, this will come up, both are unit vectors. So the only case where this is directly applicable is the set of stocks are such that R inverse has non-negative entries. This is very hard to find when you have a large n. Let's say you have 20 stocks. So trying to find out 20 stocks, of course you can find out its variance, covariance over a certain amount of a certain region. Data based on a certain time span, but then when you do the computation, making sure that the inverse has non-negative entries is going to be a big search. So if you can guarantee that, then both of them will give rise to, both are two investment strategies. Here you bring in if you have information on projected returns, you can also incorporate that here, where here you assume that returns are more or less equal on all of them. So some ideas from signal processing, because this is precisely the way match filter is designed, signal to noise ratio. So you try to use the filter for which the gain at the given instant is optimized. So here the gain is replaced by actual gain, which is the money you make divided by the volatility or the variance of what you are holding. And that leads to this solution versus the classic solution by Markowitz.